Linear actuators, in the simplest possible terms, are designed to push and pull things in a straight line. In terms of projects I build in my home shop, I generally stick with electric or pneumatic actuators. For example, when I was designing my welding table, I used electric actuators, which allows me to adjust the table up and down. I can stop it at any height that I want. And this was perfect for making myself very comfortable when welding. I've used pneumatic actuators pretty extensively. One of my favorite projects being my dust collection system. I had these small pneumatic actuators all over the shop. And I also like using pneumatic actuators for work holding jigs because they are perfect for that. There was a time that my wife was building some deck chairs for outside, and I noticed that she had this repetitive clamping of two pieces of wood together to put the screws in. So I threw together a quick work holding jig for my wife. Here's a clip of her seeing it for the first time. We've got two actuators here.
Actuators was moving this part.
Yep.
So it pushes that out, and then solenoids.
You got it. And it's all controlled with the foot switch.
Ooh, like kind of.
You can step on it.
Wait, right now?
Yeah.
Is it set up?
Yeah.
What happens? Why?
If you want to clamp something, you can do it like that. And hit it again. Then you put 3 screws in and take it off.
Can I touch it first?
Yeah.
Oh, I really is holding it.
Yeah.
Okay, and then.
Yep.
Nice! So what do you want to film?
I just did.
Jeremy, I love you.
So let's quickly take a look at how each of them work, and then we'll start to make comparisons between the two. For that, I made a transparent pneumatic actuator so that you can see what's inside. Pneumatics and hydraulics are very similar in the way they work, so we'll compare those two first. And the most basic description of this, you've got this gasket here which seals the top end from the bottom end, and if I pump a fluid into one end or the other, in this case, because it's a pneumatic cylinder, the fluid is air. Yes, air is a fluid. As that air pressure builds up, it's going to force the piston to move this way, right? Because it can't get past the gasket until it's fully stopped. And then whatever pressure you have behind it is the holding force that you're going to have here at the end. Same vice versa. You pump air into this side, pressurize it, you force the piston the other way, and you get the motion that you want. One thing that's interesting to note here is cylinders like this can push with more force than they can pull. And that's for both pneumatics and hydraulics. The reason we can always push more than we can pull is because of surface area. And let me just prove that to you real quick so this makes sense. All right, on the bottom, of course, you got the same diameter, the same outer diameter as you do on the top. But on the top, you also have the rod in the middle, and the rod is in the way. So all of this surface area you can push on, and all of this surface area you can push on. You can't push on the part where the rod is in the way. Now, of course, air pressure is pushing everywhere, right? It's pushing on both sides of the rod, but all of those forces cancel out. The only forces that matter here is in the direction that the rod is free to move, which is along the linear axis here. Therefore, we have more surface area, and since pressure is pounds per square inch or whatever units you want to use, we have more square inches over here, and therefore we can push with more force compared to this side. And that will always be the case unless you have one of those where there's a rod going through both ends, and that will make it so that the force that you can apply is equal on both sides. The reason this matters to you is because if you're operating very close to the limit of what this thing can do, you want to be sure that you can pull with enough force to get the job done, not just push it. There's another vulnerability created by this, and that is when the cylinder is in a vertical position like this, you're trying to lift the load against gravity, meaning you need the most force when you're pulling, but that's also when the cylinder is the weakest. And then when you're lowering the load, the cylinder is the strongest, and you've got gravity assisting. So in this case, you may have a situation where this will slam at the bottom and not be able to lift on the way up. These are the kinds of things that may not be obvious when you're designing your machine, but it could lead to really poor performance. So it's just helpful to know those kinds of things and try to anticipate them if you can. So assuming there are no other factors that might prohibit you from turning the valve the other way, you get exactly the opposite, a more beneficial situation. You push your load when you have the most capability. At this stage, the only important difference between pneumatics and hydraulics is the fluid is different. You're using hydraulic oil instead of air. So we pump that hydraulic fluid in, and because it's under pressure, it will force this piston to move and vice versa. And the hydraulic arm will move that way. Even though these two have very similar operating principles, the performance differences are actually pretty significant between hydraulics and pneumatics. So we're actually going to spend quite a bit of time talking about that. But before we get to that, I need to talk to you about electric actuators. The most common types use a ball screw and an electric motor. That electric motor will spin the ball screw, and then there will be an actuator arm attached to that ball screw that'll push up and down. When it comes to designing with actuators, there's some general principles that I want to share with you here. Now, we've actually talked about this a little bit in the last video. The whole video was about designing with actuators, actually, but there's some slightly more specific things that I want to share here. So let's take a quick look at some examples. This is the base unit for my dust collection system. At every one of my machines, you will find one of these automatic blast gates, which is controlled by this actuator here. Most actuators will have pin connections at the end, allowing the ends of the actuator to pivot a little bit. But in this case, I've got some threaded mounts. And over here, the piece is not shown, but there's a purchased foot that will mount right on the side of this actuator. And that foot will mate up with this custom 3D printed part. The other thing I want to point out here is that I've got it modeled in both positions. Again, we talked about this in the last video, but it's important that you see the 3D model and all the positions that it will be in when you have parts that are moving. I also want to point out, using my welding table as an example, you can see the electric actuators, which have been loosely modeled down here to represent their footprint. When you're using multiple actuators together, they will not push at exactly the same speed. There are just way too many variables that will keep that from happening, especially when you have DC powered motors like I have here. If the weight is not exactly the same, the friction is not exactly the same, those motors are not going to move at exactly the same rate. And if you watch very closely, you can see that my table doesn't raise perfectly level. You may run into issues here, and it's just something you want to be aware of, and you should not expect it to be perfect. You should plan for that in your design. I think this goes without saying, but it's probably worth mentioning that both ends of this actuator could potentially move. So even if you're expecting this end to move, if this side gets stuck or there's some kind of issue and your actuator is strong enough, you may actually break off the leg down here or have some other kind of consequential action that you didn't plan on. So it's just important to think about all the ways this could potentially move, including the way it fails, which brings me to my last point. It will be good to plan for your failure. If we go back to the previous part, I made this in such a way that this piece where the screw connects to this ABS part here, the screw should break through this part if the forces are too high, and the part that needs to be replaced is the cheapest 3D printed part, which is this part here, as opposed to breaking this much larger purchased ABS part. And because you're controlling these parameters, you can decide which is the weakest link and where it might break if the forces become too much. And since we're talking about design, I want to show you probably the most important design tool I have at my desk. That brings me to my sponsor, 3D Connection. This tool is one of the most powerful tools I have on my desk. I use this thing every day, and it's really hard to explain exactly why I love it so much without showing it to you. So I'm just going to pull up a model real quick. I was using a mouse to drag my model around like this, and then I started using this thing, and this is like holding the model in your hand. It's hard to explain just how intuitive this is, but it made my 3D modeling so much faster. I ended up getting their whole suite, but this is the thing that I would say you should look into. If you are serious about 3D modeling and you want to improve your speed, you can set up keyboard shortcuts right here on top of the keys so that you don't even have to take your hand off of it. They have another model with even more keys on it, but I prefer the 4 big buttons. This became such an important part of my workflow. I actually bought another one just so that I could carry it around when I travel. And so I have this travel version that I carry around with me whenever I go out of town. And I almost forgot to mention, I keep a compact version in my workshop as well. It's nice and heavy, so it doesn't wiggle around, but also very compact, so it fits within this little bit of workspace that I have available in the shop. I have a special link for you in the description box. If you click on that link and use the code FIELDING10, you'll get 10% off of your 3D mouse. So go ahead and order you one. You'll be glad that you did. All right, now that you know what the three options are that we're going to be discussing, let's compare those three options and see what are the pros and cons for using each one. In order to make some sort of intelligent comparison, I've picked 6 different categories in order to compare the pros and cons of each method. But of course, there are lots and lots of reasons you might choose one over the other, right? For example, if you've already got an air compressor sitting right next to where you want the machine to be, that one fact might tilt you towards pneumatics, even if electric was better. Just as one simple example. So let's start with speed. Far and away, if speed is the only factor, which it's not usually the only factor, pneumatics far and away is the fastest. You can get hydraulics that are pretty fast and you can get electric that's pretty fast, but nothing moves like compressed air wanting to fill in all those spaces when you open those valves. This is one of the reasons, among several, that pneumatics is used so extensively in mass production, because you're trying to crank out as many parts as possible, and so you need that cycle time to be very rapid. Pneumatics is going to give you a rapid cycle time. I did a quick comparison of the 3 valves that I have here, and it's obvious even at the low pressure that I'm operating my pneumatic cylinder at here, pneumatics is so much faster than the other 2 options that I have. Again, you can set up hydraulics to go pretty fast as well as electric, but there's no comparison. Pound for pound, pneumatics is going to give you the most speed. Okay, the next thing I want to do is try to compare the cost variables between pneumatics, hydraulics, and electrical systems. This one's pretty hard and interesting for a lot of reasons. First, cost is usually the most important variable. It's the one with the widest variation as well. It depends a lot on the scope of your project. So as I mentioned earlier, most of my experience at the maker, like DIY home shop level, would be pneumatics and electric actuators. I haven't done any projects in my home shop with hydraulics. In fact, I bought this self-contained hydraulic unit here specifically so that I could make this series of videos, because we're going to talk more about hydraulics in the future. This is not the only time we'll break this guy out. This is actually my first experience with like a self-contained connect the hydraulic unit to a battery and flip a switch, and it works. So this is an option, but not one I have much experience using. This is my first time tinkering with one of these. I'm used to seeing hydraulic systems which are more like this pneumatic system, where you have a hydraulic cylinder, you buy the hydraulic lines, the reserve tank for collecting the oil, the accumulator, and all these other things that you need to build out a full hydraulic system. So it was nice to jump online and quickly find something like this that was a self-contained unit. You just need to add hydraulic oil, connect some cables to it, and you can move some heavy loads with a hydraulic cylinder. So we're going to be using this for comparison here, primarily with the maker in mind. When I purchased this was roughly $30, I think. But, you know, this is everything you need to make this work, right? You just need a switch to turn it on and off, and you need to be able to flip the polarity to make it go in versus going out. With pneumatic cylinders, though, this is not going to do anything by itself. At a minimum, you need an air compressor. You need, lines to get the compressed air to this unit. You're also going to need valves to control the flow of air. Earlier, you saw me using a manual switch to change the direction that the valve could move or block the air entirely. Similarly, this is an electronic version, which will allow you to flip a switch and switch which side the air comes on in and out. I could also hook this up to a computer and program it so that it flips the switch when it receives a signal, and we get more into the automation side of things, which I discussed in the last video. There's a link to the whole series in the description. It's also worth pointing out that this is very much a budget actuator. I would not trust this in any sort of industrial application, and it's not a very good choice for automation either, even though I could automate this. The problem is when you get into those that are designed to be more robust, to lift larger loads and be more precise, they get more expensive very rapidly. As I mentioned earlier, it's really hard to compare the costs between the three directly because they're used in different applications, and it depends a lot on what you are actually using the system for as to how much equipment you need. But I'm going to try anyway. Pneumatic systems have the lowest upfront cost and generally the lowest maintenance cost. The reason pneumatic systems are so cheap is because they're really very basic in their construction. So they're pretty easy to machine and mass produce. And because they're made out of steel or aluminum and have very simple components, they don't have a lot of moving parts. They tend to last a long time. They're very robust. So that means the maintenance cost is also pretty low. Electrical systems, on the other hand, tend to have the most upfront costs, especially when we're talking about industrial applications. It's a little bit more varied in terms of the DIY hobby level, type actuators like this one. But in terms of the industrial ones, at least, the electrical actuators tend to be the most expensive upfront, but they have the lowest operating costs because electric motors only use as much energy as they need to, drive the load, whereas pneumatic systems are constantly compressing air. And if you have leaks in your system, the pressure is going down, which means the compressor has to come on again to repressurize the system and keep everything charged up. Similarly, hydraulic systems are constantly running even when the hydraulic actuator is not moving, and therefore these two tend to waste a lot more energy compared to electric actuators. So over time, you're going to get the best cost from the electric actuator. And as you probably guess, hydraulic systems fall somewhere in the middle. It kind of depends upon how well you manage your leaks, because there are probably going to be leaks in your system. They're kind of messy and hazardous in that way. Whenever you leak hydraulic oil, you got to buy new oil. With pneumatic systems, you're just using room air, which means you can dump it wherever you want and collect it wherever you want. And since room air is free, that makes pneumatic systems cheaper, especially compared to hydraulic systems where you need to purchase this oil. All right, so how about pushing force? Pound for pound, it's hard to beat the pressures and the forces that you can create using a hydraulic system. This is why if you want to shovel some dirt with an excavator or do anything that's doing some serious heavy lifting, you will usually see hydraulics over the other two systems. Pneumatics is going to give you sort of a medium grade force. You can get some pretty big pneumatic actuators, but just like we talked about earlier about surface area, the other component related to that is the pounds per square inch, the actual pressure that you can build up in your system. Most pneumatic systems are operating between 80 and 120 psi. You can get them higher than that. Hydraulic systems can have thousands of pounds per square inch. It's just all about making sure that your fittings and hoses and everything else can handle the operating pressure that you want to try to push that fluid with. Electric actuators have been improving a lot over the last few years. The issue that you run into there is with an electric motor, you generally have to either greatly increase the size of the motor, which you don't want to do because that makes the actuator huge. Remember, you need the motor right there with the actuator. Or you have to use gears to try to trade speed for pushing force or torque. In other words, if you want to push with more force with an electric actuator, the actuator has to move slower. So generally speaking, pound for pound, if you will, the electric actuators are going to give you the lowest amount of force, and hydraulics is king in terms of pure pushing force. Now, when it comes to precision and controllability, electric actuators blow the other two out of the water. If you want, you can hook this thing up to a computer. You can move it to micro inches. You got very high repeatability, putting it in the same position over and over again, stopping it wherever you want along the way. None of the other two systems compare to the level of precision you can get with electric actuators. That doesn't mean you can't get pneumatic and hydraulic systems, with reasonable levels of precision. But one of the issues that you run into is the compressibility of the fluid. Air, for example, is very compressible. When you move the actuator to the position wherever you want to stop it, the air is spongy and it's going to bounce a little bit, right? Making it a little bit difficult to get it to stop where you want. And because the air is compressible, where it stops is going to depend on how heavy the load is that's on top of the compressor, leading to some variability in where it stops. There are definitely pneumatic systems that have been designed to try to get very good precision and even stop it in various positions, but it's still no comparison to electric actuators at this point. And hydraulic actuators, surprisingly, have a similar issue. Even though the hydraulic oil is considered to be non-compressible, it's still ever so slightly compressible, especially at very high pressures. Even if you have a system designed to be very precise, depending upon the load and whatnot, and how much the oil compresses when that system is fully loaded, you may not be able to get the system to stop exactly where you want. Hydraulic systems also have this behavior that's sometimes called stick slip, where it will resist moving for a little bit and then it'll finally give and slip and move quite rapidly, leading to, very high acceleration at first. This is not even noticeable on something like an excavator shoveling dirt. Nobody cares. But this does cause problems when it comes to high precision applications where you want to move an actuator just a little bit. If it's sticking and your system thinks it's moved, but it hasn't moved, or when it slips and moves further than you expected, things like that can cause you issues if you want very high precision from a hydraulic system. Now, just like most things I've said in this video, there are exceptions and engineering workarounds to most problems that occur. With stick slip, there are special seals and other things that you can get for these various valves that will help reduce this problem. But since this video is about comparing the three systems, at the end of the day, there's still really no comparison with the level of control and precision you can get from an electric actuator. In terms of maintenance, electric actuators generally have the lowest maintenance. There's pretty much nothing to do. They just run and run. And electric motors can run quite a long time without needing any attention from you. Although when I was researching for this video, I found an article that mentioned that electric actuators can sometimes have the highest maintenance costs because of the PCBs. If you have electrical issues, replacing an electric actuator is much more expensive than the kind of things that you might replace during maintenance in a pneumatic system, for example. So the general consensus seems to agree with my anecdotal evidence that electric actuators are the cheapest, but I did find a source that said that maintenance for electric actuators could potentially be higher because of the more complex components involved. If you start replacing circuit boards, then things can get pretty expensive. Generally, those things just tend to work unless the environment is really harsh. I would love to get your opinion. If you have a lot of experience with electric actuators, share your knowledge with us down in the comment section. Do you find yourself replacing the PCBs or having to replace the whole actuator? I don't know. That would definitely be expensive if you have to do that. The pneumatic actuator would definitely be next. There's still some maintenance. You got to check fittings. You may occasionally have air leaks. You need to add oil to the system to lubricate some of the components in the system. You want the air to be dry, so you need to drain water every once in a while if you don't have an automated system for draining the water, and just making sure in general that all those things are functioning the way they need to. There's not much cost related to this maintenance. It's just things that need to be done occasionally to keep your system running in top shape. Hydraulic systems definitely have the most expensive maintenance, especially related to the hydraulic oil. You got to keep on top of those fittings to prevent leaks, because leaks are such a headache when it comes to hydraulic systems. And when they happen, and there's a pretty good chance you're going to have the occasional leak, it's something you got to take care of right away. And when you lose oil, you got to buy more oil. You got to stop everything. You got to pump that oil back in there. You got to bleed all the air out. So it's just, my experience with hydraulics has been that, maintenance is kind of a headache with those when you have to do something. But when it's working, it's great. Okay, finally, I want to cover some special considerations that might lead you to choose one over the other. One of my favorites would be noise. I tend to like for things to be really quiet in my shop, and pneumatic actuators are kind of noisy. Electric actuators are the quietest. It's also important to consider the environment that your actuator will be operating in. Are there extreme temperatures in this environment, which that may not be suitable for your electric actuator, because those PCBs and even the motor itself may struggle to operate in extremely hot temperatures or extremely cold temperatures. If fire hazards are a concern, you may not want electric actuators in a place with a lot of sawdust, for example, because sawdust is quite flammable, right? If you're processing food, you're in a Tyson chicken plant or something like that, then you really need to be concerned about food quality and hygiene. That's a great example of a place where you might want to lean towards pneumatics, or you may have to use some kind of food grade oil and you need something very special for your application, so that if there is a small amount of oil leaks, it doesn't contaminate your food in a way that's not safe. I would also say that any environment where hydraulic fluid leaking out into that environment from a hose or a valve would be considered hazardous or just unwanted, you would want to avoid hydraulics, because at some point you're probably going to have a leak in your system and you just want to be mentally prepared for the results that come from that. Another issue related to the environment is the amount of space the actuator will take up. Hydraulic installations tend to have a relatively large footprint compared to the other two systems. It's also worth mentioning that electric actuators would be the most sensitive to vibration and things like that, which might damage your circuitry inside of your actuator. So let's bring all this together in just a couple of lines. I would say hydraulic actuators are best for farm equipment, heavy machinery, anytime you want to move a heavy load, and that's the most important factor, you're going to be leaning towards hydraulics. If you need high precision, very low maintenance, and quiet, I will be leaning towards electric actuators. When it comes to high speed applications, high cycle time, you want low environmental concerns because you're just handling compressed air instead of sparking or hydraulic oil. You don't have to worry about overheating, on and on. These guys stay pretty cool. You would be looking for a pneumatic actuator. But of course, none of that means you can't use a pneumatic actuator in an application where you need a lot of force, and on and on. You can mix and match for your special needs, because that's what engineering is. It's finding the right compromise to meet your specific goals. There's no such thing as a magic bullet, one sentence answer that says, every time you have this application, you should use this, because that's just not how the real world works. In engineering, we use what we need to use to get the job done, usually trying to do it as efficiently as we can. All right, ladies and gentlemen, that's pretty much it. We've talked about all the things I wanted to cover in this video. I wanted to say before I wrap this up that I am human. I tried to cover a lot of complex topics here in a very simplistic, overcast kind of way. So if I've made any mistakes, feel free to let me know down in the comment section, and I will pin one comment to the top that tries to correct any errors that may have come up in the video. I want to say thank you to my patrons and YouTube members. You guys are a huge part of making this kind of content possible. Rather than trying to chase the algorithm and figure out what's popular, I can focus on making things that are genuinely helpful, and that's really my goal. All right, thanks for watching.